Good morning, good afternoon, and good evening, everyone from all around the globe. My name is Eric Mayo, and I'll be helping moderate today's webinar, Financial Modeling on Large Streaming Datasets. In this webinar, you'll learn how to use online stats, DataFrames, and other Julia packages to analyze larger than memory datasets from a standard laptop. The primary data example is currency conversion at millisecond resolution, with stock pricing data compiled daily over a 7-year period. We'd like to have this an interactive session today, so please write your questions in the chat. We'll either address them on the fly or address each question individually following the demonstration. With that said, I'd like to introduce you to today's presenter, Dr. Josh Day. Josh is a senior research scientist at Julia Computing. He obtained his PhD in statistics from North Carolina State University, and his specialty is creating applications and exploring new discoveries combining statistics and computer science. He maintains many Julia packages, including OnlineStats.jl, which is an excellent package for running statistical analysis on big streaming data sets. Please welcome Dr. Josh Day. Josh?
Hey, thanks, Eric. So thank you for the introduction. So I'll quick note that my slides are available in a GitHub repo, which is the link that is right here, Josh Day Talks, and then you can find the 2020 year and the streaming data webinar too, which has my updated stuff in it. So I'll add that my PhD research was in online algorithms for statistics. And just as a quick clarification, online here has nothing to do with the internet. It just means that you're operating on your input piece by piece instead of all at once. So it's a paradigm that kind of naturally lends itself to large and streaming data sets because it's not a requirement that all your data fits in your computer's memory. All right, so we'll talk about what online stats is. We'll use online stats to visualize big data and look at some of the data structures that online stats provides. And then we're going to work with CSVs and use file trees to work with multiple files at a time, and also use it to do out-of-core processing. And then we'll end with a question and answer session. So I'll try to keep checking the chat over here for questions. And if I miss something, Eric will ping me and ask and tell me to check it out. But so please feel free to keep asking questions in the chat, and I'll check that from time to time here. All right, so what is online stats? So it is online updating for a wide variety of statistics, models, and data visualizations. So there's a lot of stuff in there. We'll only have time to cover some of the more basic things, but if you're interested in more, please check out the documentation. So it has some parallel computing primitives, which we will cover, and it makes big and streaming data analysis pretty easy. Again, since there's no requirement that your data sets fit in memory, you're allowed to work on much bigger data sets than you would otherwise. So Online Stats has two basic operations that kind of make up the gist of the interface. And so the first operation is fit. So if you look at this top box here, so every statistic in Online Stats is its own type. So there is a mean type in Online Stats. And so we can initialize this and we can see the number of observations is 0 and the value is also 0. And then we can update it with the fit function with new observations. So we can update it with a scalar, like here, we're updating it with the number 1, or we can update it with multiple observations. So here's 2 and 3, and now our output says we have 3 observations and the value is 2. So the second operation that Online Stats does is merge. And this is how we combine multiple statistics of the same type into one thing. So here, let's make a second mean object and fit this mean with new data, and then let's merge it into the first one. And so our first mean we fit on 3 observations, the second one we fit on 2. When we merge them together, they have 5, as we would expect. So this is what facilitates the parallel processing capabilities of Online Stats. And that's because if we look at this diagram down here, if I take 3 mean objects and fit them on subsets of data and then merge them at the end, well, that's analytically equivalent to fitting just one of these mean objects on all of the data together. So if our problem is easily split up, or maybe our sections of data don't all fit in memory, we can still kind of get the same answer at the end. So here is a big wall of text on kind of what online stats can do. And the way that I worked on this package in general was starting with some of the basic things in statistics and figuring out like how to do them in an online fashion. So a lot of things are basic, like means and variances and quantiles. Actually, quantiles is a kind of a harder example. But we started with some basic things. I moved on to some other kind of like statistical concepts. So reservoir sampling is how you take a random sample of a data stream. Statistical bootstrap is how you calculate estimates of variance of various statistical estimates. There's a lot of tools for doing machine learning. There's some more kind of database-y operations. So we're going to take a look at group by operations today. And then hyperlog is how you get an approximate count of distinct elements when you're working at a data stream and you don't have all the observations all at once. And then there's also parametric distribution fitting for a whole bunch of statistical distributions. Okay, so for our first example here is let's talk about visualizing big data. So how do we do this? So visualization is a requirement for data analysis. It's just immensely important. So when we have big data sets, we still want to be able to plot them. And so how do I even plot a data set that doesn't fit in memory? So one option is, doing cloud computing. I could go rent some more RAM on, AWS or some kind of cloud provider. I can buy some more RAM for my own computer. But those are, well, one, kind of expensive options. And ideally, I would just be able to do these things on my own laptop. So we're going to look at two types in online stats. And so these are partition and index partition. And they're both ways of plotting like infinitely sized data sets. And we're going to start with an animation that shows how this is working here. So this is a Pluto notebook. So if this notebook is available in that GitHub repo that I posted in the beginning there. And so one thing I just want to note about Pluto notebooks is that so a lot of the code I'm using is hidden. And so you won't be able to see some of the things. And if you're used to Jupyter notebooks, the output actually shows up on the top of the code rather than the bottom. So if you're unfamiliar with Pluto, it just works a little bit different. And I just wanted to kind of address that before we start looking through this. All right. So the partition type is for plotting a univariate data stream that's possibly infinite in size. And so the idea is that we take a fixed number of bins, and whenever a bin fills up, we merge some of the older bins. So in this example, I am combining a mean and the extrema. So the extrema is going to give us the minimum and the maximum. And excuse me, the series type is how we combine stats together. And we're putting this inside of a partition with 20 bins. And so if you look at each of these kind of rectangles that are showing up here, so what these are representing is, so the width of a rectangle is how many observations are inside of that bin. And then the height of that rectangle is the minimum to the maximum of the data that is contained in that bin. And there's also a little blue line in the center that represents the mean. So as this grows to infinitely many observations, I wouldn't want to plot the actual data, right? So if I have a billion observations, that's not something that like my GPU is capable of plotting and visualizing. So one way to think about this is a way to plot a coarse view of your data. So you'll notice that each of these boxes kind of fully contain all of the data points. And so while we lose some information, I'm sorry, excuse me. There's a loss of information, right? So since we're not looking at each of the individual points, we're looking at kind of these cross sections and data that's summarized with statistics. But it gives us an avenue for plotting these things where otherwise we wouldn't be able to plot something that kind of grows infinitely. And let me just check the questions there. Oh, sketch-based. So there isn't other sketch-based algorithms in online stats, at least as of yet. just to answer the question right there. All right, so that is partition. And again, that's for kind of univariate data. The next thing we'll look at is index partition. So this is for bivariate relationships. And so it uses a similar idea to up above, except now we're plotting an X variable and a Y variable. And so we're still looking at these cross sections, kind of these vertical cross sections across different values of the X variable. But now we're looking at a different variable altogether. It's not just the number of observations. And so the idea here is that, once we run out of bins, so in here I'm looking at, so this is a histogram with 20 bins. The index variable is a float, and I'm using 50 bins. So once I run out of space in one of my bins, I merge the two nearest bins that are closest to each other. So it's non-deterministic in the sense that you don't know where these bins are going to end up. But again, it allows us to get a coarse view of our data set where we otherwise wouldn't be able to. So one thing to note here is that this is a plot of 100 million observations. So if I were to just do a standard scatter plot of this, my computer would kind of completely choke because my GPU wouldn't be able to handle that. But again, this gives us a way of visualizing something that's very large that we otherwise would not be able to. Okay. All right. So that is how we visualize big data. All right. So now that we can plot it, where does the data come from? So one thing that online stats, or which is, I guess, neat about Julia, is that online stats is allowed to be agnostic on the source of your data. So online stats can work with kind of any kind of iterator in Julia. So as long as some other package provides an iterator off of a data source, online stats can use it. So we're going to be looking at the csv.jl package. So there's some great utilities there. It's an extremely fast CSV parser and has some great utilities for iterating through files. And so why are we working with CSVs? So for better or worse, it's a standard format, even though it's not the most compact as it could be. And again, just because of kind of how Julia works, the CSV package and online stats are able to work together, even though they don't know about each other, just because we're relying on multiple dispatch and working with generic iterators. All right, so let's see how online stats and CSV works together. Excuse me. Sorry, I'm getting over a cold here. But anyways, all right, so we are going to look at Kagel's huge stock market data set. So this is, so I think all historical data for 7,195 individual stocks that are traded in the US. So this is OHLC, open, high, low, close data for every stock. And they're all contained in individual files. So altogether, this is over 700 megabytes. So this is something that my computer can handle. I'm running on, I have 8 gigs of RAM on my MacBook Air that I'm currently streaming this on. So I'm not actually running out of memory or anything with this example, but we can kind of imagine at least for a moment. So here is all of the text files that we're looking at. So they all kind of have this name where it's the stock and then .us.txt. And they're all CSV files. So if I load one of these files, I can see this is what we have in there. So we have the date, the open, high, low, close, volume, and I'm not actually sure what open int is, but it always seems to be 0. And then one thing to note is that the stock name isn't a part of the data set. So the stock name is getting from the file name. All right, so let's try getting statistics, or in this case, we're going to make a plot, and we're going to do it directly from the CSV file. So the CSV package has a file type that will parse and do get all the type information and kind of give you an object that you can iterate through by row. So here I'm creating a function where you enter in the stock, And I'm going to create an index partition. So the index variable is going to be the date. And then I'm going to use the extrema again, and I'm going to use 300 bins. Then I'm going to create this file object. And then here I am just creating an iterator that's going to iterate over. So first I'm going to make a pair. So this is the symbol for a pair in Julia. So the pair is going to be date and the low, and then the date and the high. So after I've fit the low and the high for every single day in my data set, my extrema, the minimum and maximum, is going to capture all of the observations. So I'm going to fit this index partition on this iterator, and then I'm going to plot this all together. And so I just kind of randomly pick a few stocks that are, well, somewhat interesting. So these are Apple, Microsoft, IBM, Google, and Netflix. And then again, if you're not familiar with Pluto, Pluto offers some really cool things for interactivity. And so here I'm creating just a little drop down and selecting one of the stocks from this list of stocks. And then I'm going to call this plot high-low function, which I've implemented up here. So there is Apple. I can click Microsoft. And so Pluto notebooks are, here we go, observable notebooks. So when I make a change, it kind of makes other changes downstream. So when I change the stock to be IBM, this plot high-low function is getting called with IBM. And so one thing to note that all these operations are happening on the fly here. So I'm loading the file, and then I'm iterating through it and calculating these data summaries and plotting the index partition. Okay, so there is kind of one problem with this approach. So we talked about how this data, all this data together is 700 megabytes, which isn't a problem for my computer, but let's pretend for a second that it is more, like more than my memory allows. So csv.file loads the entire CSV. And so even though we're using online stats and we only need to be looking at one observation at a time, CSV file is loading the whole thing all at once. But luckily, CSV offers a rows object, which lazily reads row by row from a CSV. So it has a super small memory footprint because we only need to load like one row of that CSV into memory at a time, but at the cost of we don't get any type inference. So instead of something is showing up as an integer or a float, everything is going to essentially show up as a string. So when we get these values in, we have to parse them into values. So here is a second function. It works very similar to the first one. So we're starting with this index partition, and then instead of CSV file, we are going to look at CSV rows, and we're going to add this keyword argument reuse buffer equals true. And so what this does is it uses the same memory to load every single row. So every single row goes into the same section of memory. And so this is the absolute like least amount of memory that we could use while iterating through the CSV file. So we're taking for each row, we're going to take the date field and we're going to parse that as a date. We're going to take the low value and parse that as a float 64. Same thing with the high, parse that as a float 64. And again, we will fit this index partition with that low and high value so that the minimum and maximum of the extrema totally capture all of the data in that bucket. And so there we go again here. So here is our second function where we have, so there's Apple, let's do Netflix. Yeah, so now instead of loading the whole file all at once, this is actually iterating row by row over a CSV file. And so now we're kind of like using the power of CSV and online stats together. So we're hardly using any memory at all, even though we're going through a couple kilobyte file. Or yeah. Okay, and oh, someone has a clarification. Open int is open interest. Usually only applies to options and features. Got it. So here's another question. As you said, the mean can be partitioned thanks to its definition. Summing does not care about ordering, but how do you handle the other operations you mentioned if you perform them one slice at a time, e.g. fitting? Roberto, I'm not sure if I completely follow this. What Well, so maybe this is a clarification. So not everything in online stats can be merged together or even fitted analytically. So means and variances and I mean, lots of other things are things that you can update analytically. But for certain things you can't. So for example, logistic regression does not have a closed form solution. So it requires an iterative procedure in the offline case to get the parameter estimates. So in those cases that we have to approximate things, we use a stochastic approximation, which is a whole big field of research. But so not everything can be merged or fitted analytically, is what I'm saying. All right, so one more question here. I could easily read the CSV to the plots without worrying about big data that doesn't fit memory. Can you clarify exactly how the methods you're showing avoid keeping data live in memory when it's too big to fit? Gotcha. So we can pretend for a second that this CSV file that I've loaded here, like just imagine that that CSV file by itself is too big to live in memory. So it's completely possible to write to a CSV file, and you could end up, since you're storing that on disk, I could write to a CSV file on my computer, and I could end up with a 20 gig CSV file. So I would not be able to load that all into memory at once, or at least without a whole bunch of crazy swapping that my OS would have to do. So this is a way to work around that. So instead of loading that whole file into memory at once, I would only be loading with CSV rows, one row at a time. And so the impact on my RAM would be negligible, because we're only looking at one small piece at a time. But we're able to plot then all the data essentially together, even though, or whatever statistic we're doing. But we're only looking at one thing at a time. Okay. So if that didn't answer your question, just keep asking questions in there, and I'll keep answering them. All right, so what about working with many files at once? So this is a common scenario, right? So a lot of sources kind of publish, weekly or monthly reports. And so it's pretty common that, like, all right, we want to take all the files that are, all the historical files up until now, load those into memory and do some kind of analysis on it. All right, so now how can we analyze multiple files at once? So for that, we are going to use Trees.jl, which is a relatively new package by Shashi. So he wrote JuliaDB and also Dagger, which I'll talk about in a moment here. But so FileTrees provides file tree abstractions with easy parallelism. So it's a way to run operations on a collection of files that are, in possibly nested directories on your computer. It's got a really simple and kind of neat syntax for operating on subsets of trees, which we'll look at. And then it's powered by the same technology that's behind JuliaDB, which is Dagger, which kind of does the parallel processing stuff. So I'll note that in the previous version of this webinar, I was discussing JuliaDB here and not FileTrees. So I think FileTrees is kind of a more generic solution to the problem that JuliaDB also solves. So JuliaDB is a way to kind of do the same thing, but it requires you to load all of your files into a specific format, and FileTrees is a little bit more generic, and it's just a little bit more flexible. So the basics for file trees is there's kind of four things to know about. And so there is this file tree object, which you start by kind of initializing for a path. You create the file tree. You create a load function that can either load them lazily, or it can kind of load them greedily onto your computer. And then we can map functions over every file in the file tree. And then we can also call reducing functions. So it's a way to do essentially map reduce jobs over file trees. So for an example, we are going to do a group by operation on many files together here. And I'll check back on the questions right after this example. All right, yeah, so for further motivation, only being able to work with one CSV at a time is a huge limitation. So we're going to use this file tree object to work with a whole bunch of them at a time. So remember, we are working with like 7,000 some files. Where did I say that? Okay, yep. So we have 7,195 individual files. So we could, kind of do something like this and then load every file individually. But then we have to have some kind of crazy loop where we're doing this 7,000 times. So it's much easier just to create this file tree structure and then work with that. So I mentioned there's a neat syntax for working with subsets. And so once we've created this tree object, we can now select files inside of that tree using, so this is the glob string macro. And then we can also use, regular expressions. And I think there's even a few other ways to match different subsets of stocks or different subsets of files inside of a file tree. So one neat thing that file tree does is it makes it very easy to kind of do lazy operations. So let's first take a look at this function here. So I have my file object, my file tree object, and I'm going to be using this subtree for now just as an example so that we can print all of the items that are in it. And so again, we're looking at Apple, IBM, Microsoft, and Netflix. So we've created the subtree here, and then on the subtree, we're going to call load, and we're going to load it with a function. It's going to take a file as the argument to that function. And we are going to load it inside of a data frame. Then we're going to add a field to that data frame called file and give it the name of that file, and then spit out that data frame. So once I call this function, we still have the same tree structure, but now kind of the nodes of that tree are not files, they are data frames. And so now let's say, all right, so we want to analyze all these things together. Oh, sorry. So let's see like which one has the highest maximum price. And so we are going to map values. So this is going to be a function that's applied to a data frame, since the nodes of our tree here are a data frame. And we're going to take the maximum of the high field of this subtree DS here. And so we can see now we don't have a data frame, we have float objects. And we can ignore this exec for now because that only matters if we're operating on things lazily. So it's going to just do the identity for now. So this is the same as what's up above. And we can call get on one of our files in order to get the value. So Apple's maximum price for the data that we have here is 175.61 per share. So here is this. I'm binding a value be lazy. And so when the checkbox is empty, this is false. So I originally loaded all of my data frames with lazy equals false. So let's just try turning that on to true for a moment and see what happens. All right, so now we no longer have a data frame that is in the tree, but we have a thunk. And you can think of this as like a function that hasn't been run yet. And so Julia knows that there's a function that we have to run, but it hasn't been run yet. And then when we call map values on a tree of thunks, it makes a thunk of a thunk. So you get these kind of nested functions that Julia knows about, but hasn't actually run yet. So there is kind of this nested order of operations that Julia needs to do. And Julia will actually run them when you call exec on this tree. And the neat thing about when you call exec here is that this all happens in parallel if you've started Julia with multiple procs. And Pluto says this is still loading here, but so something must have gotten hung up. But anyways, so once we have the thunks here, once I actually execute this, yeah, these floats will show up and it'll be the same as if we did not do it lazily. Okay. So let's try answering a question here. So what is the average range for every stock? So let's say we're interested in the volatility of stocks, and we think that the average range is a good measure of volatility. It's not really, but we're just going to use it as an example. So we are going to take our big tree now, so the one with all 7,200 or so of our files, and we are going to load all these into separate data frames. So once we have all of our separate data frames, so remember this was about 700 megabytes, so this all fits in memory for me. I'm now going to call it reduce values on all of the data frames, and we're going to concatenate them together into one big data frame. So here is the first stock is A in here, and so there's that first data set, and we can glance down here and say, okay, so we have 14 million observations of all of our stocks are now combined into one big data frame. So inside of the data frames package, we're going to use the group by function to group everything by the file name, right? So that is identifies which stock we're looking at. And then here we're going to calculate the mean absolute difference between the high and the low. And so now we have this big dictionary that gives us all of the average range for every stock in here. There we go. And so now I can look at the various pieces of this. So let's look at, here's Microsoft, there's Netflix. Cool. All right. So that was kind of the way that we do it if we have enough RAM. So again, so I loaded all 700 megabytes into my memory all at once. Ideally, I wouldn't have to do that. And so I'm going to combine a few steps here, but now I am setting lazy equals true. And now instead of even loading these into a temporary data frame, I'm just immediately, for every single file, I'm going to create a dictionary that gives the file name, and it has as its value the mean absolute range of that data set. So for all 7,000 files, we're making 7,000 dictionaries, which all of these values, and then we're going to reduce all of those dictionaries with merge. So we're going to merge all of these dictionaries together into one big one. And so again, so these are all thunks because they're operations that haven't happened yet. And then once I run exec, Julia knows how to execute this, and it does this in parallel. And now I have the same result as before, but now I've done this lazily where I haven't loaded everything into memory all at once. Oh yeah, and so there is some of our stocks right there. Okay. All right, see how we're doing on time. All right, we're doing good. So I've got kind of two more examples here. And so one is a big data example, and then one is, I guess I'm calling this an infinite data example. And so we're going to use the true FX API. So we'll discuss that in a second. But the idea here is that at regular increments, we're going to load a statistic that we've saved. We're going to update it with a new value, and then we're going to save it. So one idea here would be that, so if you're updating something in real time, you're going to have to save that probably in a database somewhere. So instead of using a database, I'm just using the serialization capabilities of Julia. But more on that in a moment here. So the TrueFX API gives you foreign exchange market data, and so it's infinitely sized because it's arriving in real time, and we can continually hit this endpoint over and over that they provide, and gives a bunch of data on this foreign exchange market, which I'm actually not too familiar with. I think some of you who are participating in this probably know more about this than me. But anyways, so I am using the serialization features of Julia to save a group by. And so here I am grouping by string. So string is going to be the pair of currencies that I'm looking at. And then expanding hist is a histogram that will kind of automatically fit in different data. And let's see if, let's rerun this for a moment. And in Pluto here, I have a little clock, which is, and so once the clock ticks, so every, let's go 2 seconds for now. So every 2 seconds, I'm going to deserialize that statistic. So we're going to deserialize this from disk. We're going to call my getTrueFXData function, which is up here, which reads, takes the CSV data from this endpoint. And then I'm going to fit my statistic on that data that I've just retrieved. And then I'm going to save it back to disk. And then I'm going to plot the values. So let's just click start here. And here we go. So now, so I guess the thing that I'm plotting here is bid points, which again, I'm not even too familiar with. I don't even know if this is a super useful thing to look at. But the idea here is that we're kind of collecting this data in real time. And if you're trying to perform arbitrage or something, you might be looking at a set of currencies and trying to figure out what avenues you have for making money. But so this is, yeah, this is the stream of real-time data. I mean, we're looking at it every 2 seconds here. But so every 2 seconds, again, I am loading my statistic from the disk. I am calling that endpoint to get new data. I'm updating my statistic with new data, and then I'm saving that statistic back to disk. And so this is one way to work with, yeah. So again, this works with infinitely sized data. One more thing, I guess, that I haven't mentioned for online stats is that, so I have a requirement that all the algorithms have to use constant memory. So the memory requirement can't grow as your observations grow. So for anything that you have input into online stats will never run out of memory. Yeah, okay, so now we're starting to see the shape of these distributions here. All right, so the next one we're going to do here, so this is an actual, so like, I guess I would call this a big data example because I'm using more data than I have space in my RAM. So again, I have a kind of a lightweight MacBook Air with only 8 gigs of RAM, and I'm looking at this New York City taxi data set, which has over 9 gigs. And so I have already, let me just stop this so we don't choke my computer. And so this data set is gives some kind of basic metadata about every single yellow taxi trip in New York City. And we're going to look at 2018 here. And so there is one file for every month. And oh yeah, so this is the approximate size. All right, so this is, well, not approximate, this is the exact size. So this is, so the CSV files altogether are about 8.5 gigs. And so if I just load the first file in this data set, this is what it looks like. So there's vendor ID, which we don't know what it is. There is the pickup time of the ride. There's the drop-off time, the number of passengers, the distance of the trip, a few other kind of metadata things. I think also the price of the fare is also in there as well. So the question that we're going to ask is, what is the distribution of passenger count by date? So maybe we think that people are more likely to share a cab in the winter than the summer or something like that. So we're going to try to calculate this all together with a big group by operation. So I've done this in 2 ways here. And so the first way that we're going to look at, and so I've already run this notebook, is kind of I guess the dumb way to do it. So we're going to take our group by, so we're going to group by date, and we're going to get a count map. So this gives you the count of distinct elements, and we're going to iterate through the passenger count. And so we're going to get like the number of passengers that were 1, the number of passengers that were 2, and so on. So the first thing we're going to do is we're going to iterate through the files. So for every single file in this path with all of my files together, I'm going to take a CSV rows object, and I'm going to iterate through the rows. And again, I need to parse the date, and I need to parse the passenger count. and then I need to fit that statistic. And then when I go to create, when I actually call this function, so you can see on the bottom right here is the time that elapsed. So kind of doing it the kind of the dumb kind of serial way, this took 290 seconds. And this was on the first run, so that includes compilation time, but that should be pretty minimal in terms of the overall time spent while running this. So now that we've calculated the distribution of passengers for every single day, we can type in, whatever day that we want. So there's what it looked like on June 1st. There's June 2nd. And we can kind of look through any given date and look at what the distribution of passenger count was. Which some of this data, I don't know if I believe, because I don't think you can fit 8 people in a taxi, or 9 people in a taxi. Or 0 for that matter. Anyways, so the other way that we can do this is let's use the file trees. So again, here let's create our tree, and we're going to use that same path. And so there are our 12 files for every single month. And now the function that we're going to do is we're going to create our group by object. We are going to create our iterator, which is starting to look a little bit messy and go onto multiple lines because we have to parse the values again. And then we're going to fit that statistic on that iterator. All right, and so now we're going to call reduce values on this thing. And so this one took 219 seconds as opposed to the serial version, which took 290. So I'm a little bit unfamiliar with how Pluto works, and I'm not sure if it automatically starts you with multiple workers or not, because I was actually a little bit surprised that this was that much faster. Because if you start with only one worker, there's a little bit of overhead in communication costs if you do parallel processing on a single worker. But anyway, so this file tree version ended up being faster, but Pluto might have started me with several workers to be with. And again, we end up with our same data. So now for every single date, again, we can look at what the ride or the passenger count was. So there is December 1st. All right. And that's all I have is in terms of examples and everything else. So thanks for watching and participating. I'll stay on for the time being and answer any questions that are there. But yeah, thank you for attending.
Josh, I have a question.
Yeah.
Could you bottle up each one of these examples and basically run it as a standalone application for somebody? So could they go in and do each one of these things?
Yeah, certainly. Yeah, absolutely. So it depends on if you want kind of a user interface, which you could do with Pluto or Dash or some of the other things that are available in Julia for making kind of web app like stuff. But yeah, but it would be very, very possible to do that.
Thank you.
Mm-hmm.
So we're getting a lot of thanks from the folks out there. No additional questions that I can see yet. Oh, here we go.
So I got a message. Is file trees available in Julia 1.5? It should be. Yeah. So I think I'm actually a few patch releases behind. Yeah, I'm running on 1.5 right now. Is there a way to specify how much memory online stats can use? I think not directly. You might be able to do something. There might be a flag when you start Julia that can set that. Could we do a hyperlog log example? Sure. Yeah. Let's do using online stats. And let's make our hyperlog log. And let's fit it on 210. Let's see. How many different values we want to do? Okay, let's do 10,000 values and let's do it 10 to the 7. All right, so we're going to have 10,000 unique values, and oops, hold on, before I do this, I need to tell hyperlog what the data type is that I'm looking at. And so we're going to have 10,000 unique values, and we're going to fit over 10 million times. There we go. All right, so that's pretty close. So our exact count was 10,000, and we got to, well, only 15 short of 10,000. So that's pretty good. Yeah, you'll also notice that it's very fast. Yeah. Mm-hmm.
Hi, Josh. It doesn't look like we have any further questions coming in. I certainly appreciate your time. Thank you so much, Dr. Josh Day, for walking us through these examples, and hopefully people will have questions. Feel free to reach out on Discourse channel, or possibly send us an email if you have some more pointed questions for your organization. You can email us at sales@juliacomputing.com. Thanks a lot for your time, Josh. Appreciate it.
Yep, thanks. Thanks, everyone.